Welcome to the 20th lecture video for Physics 4A. This is our single lecture this semester covering Newton's law of universal gravitation, on which we regrettably have very little time to spend this semester. We start with a little history lesson on geocentrism and heliocentrism, presenting both as a scientific theory of their time. After this introduction, we spend some time making sense of Kepler's three laws of planetary motion, which he figured out by analyzing Tycho Brahe's data, and which marks the beginning of modern astronomy. As unlike the Copernican model, Kepler's laws are still useful in figuring out motions of objects in our solar system, up to a reasonable approximation. After this long introduction, we finally introduce Newton's law of universal gravitation as the fundamental law from which we can derive Kepler's laws mathematically. There are many things we would like to do with this new law, but in this short 2-hour lecture, we have to be satisfied with the derivation of the escape velocity formula and the derivation of potential energy expression for the inverse square law. We rely on your next class, covering electrostatics, to teach you much more about physical laws in the form of an inverse square law. But let me add an optional lecture next to it for anyone interested in additional topics and problem solving involving the law of universal gravitation, including a derivation of the geosynchronous orbit and more.
So what I want to use a little bit of time right now, maybe 10 minutes, is a little bit of a history lesson, or going over some history that you might already know. How many here have heard the name Galileo? Good. How many here heard the name Aristotle? Okay, good. How many here have heard of Copernicus? Okay, Jared, what is Copernicus known for? Okay, somebody who remembers what Copernicus was known for? Stephen? No. Okay. So I was going to. Okay, then let me ask for three more names. How many here have heard of Ptolemy? How many? No one has heard of Ptolemy? It's a Greek name. What was Ptolemy known for? Okay. How many here have heard of Tycho Brahe? And the third name was going to be Kepler. Okay. So, where have you heard of Kepler from?
Some science.
Yeah. By the way, a lot of NASA stuff are named after these guys. There's a Kepler probe or something. So anyways, so the reason I want you to go over this history lesson, which is covered here, and expand it out a little bit more is you have some sense of sort of history of science from having gone through school as a student in the 21st century or 20th century. But I think a lot of people come away with an impression that's not 100% accurate. So I want you to, now that you are in, calculus-based physics class, I want to make sure that your impression of the history of science is correct. So let me ask you some simple question that I think most of you know the answer to. So this is the question behind the geocentrism versus heliocentrism. So we are, standing on Earth. And you look out in the sky and you can see the sun. So considering that sun and earth, which is at the center? Or if you want to consider one of the two as not moving and the other one as moving, would you say that it's the earth that's at the center, meaning earth is the one that's not moving, and it's the sun that moves? Or would you say it's the sun that's at the center, as in it's not moving, and it's the earth that moves? Like, what's the answer? Is it the sun at the center, heliocentrism, or is the earth at the center? Most of you will say it's the sun at the center. Does that make intuitive sense to you? It's the earth that does moving? Does it feel like the earth is moving right now to you? No, right? So why do you say then the sun is at the center? Diagrams? I can draw diagrams of Earth being at the center here. In fact, that's one of the diagrams I do have loaded up. So if a diagram is the reason you believe it, then here's a diagram that shows Earth at the center. Yeah. So why don't you believe this diagram?
Some of the planets don't exactly cross across the sky
Yeah.
in a straight line.
So this is a scientific question. Is the Earth at the center or is the sun at the center, right? And for most of our written history, the proposition that made most sense to people was the proposition that Earth is at the center. It actually takes a lot of modern science for you to actually agree that the sun is at the center. Instead of just believing someone based on the authority of them telling you. Like most of you think the sun is at the center because that's what you've been told since a very young age. And if anybody ever said the Earth was at the center, they were ridiculed out of existence. And I mean, I don't mean to say heliocentrism is wrong. It's not wrong. But the attitude that you approach it with can be wrong. So what I want to first to show you is that geocentrism was actually a scientific theory. It's not something that comes out of mysticism. It's not something that, there are religious things associated with it, but the origin of geocentrism is the Greek philosophy. It's not the modern science, but it's still scientific attitude that was at the basis of geocentrism. So, when you look, so this is the diagram, that shows Earth unmoving because that's our experience. We stand on Earth, and it doesn't look like Earth is moving. When you look at the sky, it does look like the sun and the moon, they do move. So you put them in an orbit around the Earth. So the sun goes around the Earth once a day, and moon, for whatever reason, moves much slower. It goes around the Earth maybe once every 28 days, right? That's what this model says. And the ancient astronomers, they found these things that they called planets. Does anybody know the difference between planets and the planets like Venus, Mars? Difference between planets and the stars, these stars. Like if you were an astronomer just looking at the night sky without any telescope, just looking at it with the naked eye, does anyone here know what the difference would be?
They don't twinkle as much.
So there's the twinkling. When you look at the stars, they twinkle as in when you look straight at it, you are not blinking. The starlight would go like out and in for some reason. And the planets, all right, they don't twinkle as much. But even the stars, sometimes they won't really twinkle. It's a matter of atmospheric condition.
They're only visible certain times of the year.
Stars?
No, the planets.
I see. So planets, they don't match the seasons exactly. But it does have something to do with stars. They are unchanging. When you look at the night sky, you will always see the same pattern of stars. The patterns that's visible at any given time of the year might change. So we are in the winter right now. So when you walk out at 10 p.m., after your lab today, or 9 p.m., then in the sky, what you will see most prominently is the constellation called Orion. Orion looks like this. Orion's belt and two stars like this. Like it's a big pattern that you will notice. Once you notice these three stars in a line, you will see that all the time, every time it's winter. And in the spring and summer, you will see different set of constellations. But that's what ancient astronomers imagined, that the stars are a pattern of light that's embedded into this celestial sphere. And the celestial sphere rotates around the Earth once every day. And this background of stars do not change. Okay? And what distinguishes planets is that their positions change. That when you can imagine yourself as ancient shepherd or whatever. At night, you have to watch the ship. You have nothing else to do, so you look at the stars. You start to notice these patterns, notice the patterns like this name them Orion, attach them to some mythology about a hunter. And once you start to recognize these patterns, then what you will see is that every now and then you see a spot of light that doesn't belong in this pattern. And if you keep watching them day over day, you notice that those lights, they move across this pattern. And that's what people named as planets. So these are called planets. And it comes from the Greek word. I forget the exact origin word, but the English translation would be wanderer, because they move through the sky over a very long period of time. So for example, if you look at position of Mars, for it to go through the one full cycle, it would take about 2 years. So it's not exactly seasonal, but when you look at the night sky day after day for over a month of time, you would start to notice that these don't appear at the same position each night. So the Greeks had a long time to think about this, and they came up with what we would today call scientific theory. They came up with a hypothesis that this is the model that explains why some of the light you see in the sky moves. You call them planets. They move because they are on their own orbit. And how fast their orbit goes is different from how fast this orbit of the celestial sphere goes. Yeah? And so this is something that would be covered in an astronomy class over a day or 2 days. Like Astro 10, they would spend a day or two covering this. I'm just trying to go through this quickly. There's a couple things that's odd about the motion of these planets. So I'm just gonna make up a figure. I'm pretty sure Orion is not in this the path of planets. So don't judge me for doing this, but I'll just pretend that Mars is at one position at a particular night. Once again, I'm not claiming that this is anything you would see on a real night sky. In fact, I'm pretty sure you won't see this, but just imagine that Orion, this is one of the constellations that's in the actual path of Mars. So over a period of a month or so, what you would see is this Mars appearing at different positions over a period of month or so, or a long enough period of time. And all of this so far matches with the model that we have built, right? You say, all right, so Earth is at the center, and the Mars moves at some particular rate, and the rate at which the stars move, the sphere containing the stars rotate, is different from rate at which the circle that the Mars is on moves. That's why there's the alignment between them changes over a length of time. Now, here's the strange thing that ancient astronomers would notice, because they are good at observing details. They would notice after a while. They would notice that this motion of planet, at some point they would slow down. And for some brief period of time, maybe about a month or 2 months at a time, they would actually go backward for a bit. So it was moving this way initially, and over some period of time, it would go backward. And then at some point later, it would resume the forward motion. This is given a name. In case you are interested, look it up. It's called retrograde motion. Retrograde motion. It's called retrograde for the same reason that if a fashion is retro, it's like backward. So if this is the normal forward motion, then this is a backward motion. And this motion is puzzling to the early initial geocentric model, as in you can't really explain it based on here. So if you are sticking with this model, then what Edward said would work. There's a motion of the planet that you simply cannot explain with this geocentric model. Now, what I will tell you is that, so all of these were noticed by Greek philosophers 2,000 years ago, actually more than 2,000 years ago, like 2,500 years ago. So, this is not new to anybody who's actually observing the night sky. So they came up with a solution that's still intuitive to them. This is where Ptolemy comes in. So, so I gave you, I threw out some names. Let me write them down here, and I'll explain. So the names I threw out were Aristotle. I'll try to write them down in chronological order. Aristotle, Ptolemy, and then later on you would find Copernicus. And Galileo is the famous name that most people know. But the people that I really want to bring your attention to in a few minutes is actually Tycho Brahe, and I may be misspelling some name. This is the name I think I'm misspelling. Kepler is the name that I probably won't misspell. This is the important name. And so let me just write down a brief description of what each of these are known for. Aristotle is actually known for a lot of things. If you ever take a philosophy class, you will hear a lot about him, and a lot of things we still think about in philosophy still comes in from Aristotle. He was like student of Plato, was student of Socrates. In physics class, he's almost always a butt of a joke because almost nothing he said about physics is correct. Nothing he said about motion is correct. Nothing he said about astronomy ends up being correct. But he's the one who's credited with the geocentric model. So we will credit him with the initial geocentric model, which fits our intuition well. And that's I think why Aristotle is kind of a butt of a joke in physics class, because a lot of things he says fits our intuition. So when he says something about philosophy or, I don't know, writing, poetry, things where you rely on your intuition, what he says makes a lot of sense, and it's valid for a long period of time. But a lot of things in physics actually don't make sense. It doesn't make intuitive sense. That's why we have to spend so much time trying to develop your intuition. And that's the same reason why this is a great Greek philosopher. Not a dumb guy, he's a smart guy. But he was almost wrong about almost anything he said about physics, because he was relying on his intuition alone, and he didn't have all the empirical data or the mathematical tools that we take for granted today. So Ptolemy is the one who actually improved this scientific model of geocentrism. So he came up with a model that accounted for this retrograde motion. So if you are looking for something to just look up, what you can look up is the phrase epicycles. I think I have a picture of an epicycle somewhere here. Yeah, so this is an illustration of an epicycle. So let me erase this board so that you can see it better. It's not any bigger. Okay. So this is an illustration of an epicycle. So the epicycle means just on the circle. So what Ptolemy did was he put another circle on top of the circular motion of the Mars. So imagine this red circle is Mars. Then in the original geocentric model, Earth is, why is Earth not at the center? Well, let's say Earth is at the center, and Mars, which is on a circle that's going around the, Earth, there's another circle on top of that. And so according to the Ptolemy's model, how we see Mars is a result of the rotation of these two circles. Then you can imagine how, depending on their relative motion, there will be at some point along this motion, this Mars would appear to be moving backward. When Mars is, let's say, on this portion. So let's imagine that this circle rotates this way, and this circle also rotates this way. Then when Mars is on this portion of its motion on the epicycle, then these two can combine in a way that it generates this backward motion. So this problem of retrograde motion was solved by using this model called epicycle. And this model has been actually in use for thousands, well, more than 1,000 years. Ptolemy came up with it, I don't know, sometime BC, sometime more than 2,000 years ago. And it wasn't until around the 1500s when this was getting challenged. And I guess the whole story of why this started getting challenged is a little bit of a too long story to go through. Comes down to over that long period of time, 1,000 years, they had to keep modifying the model to make it continue to agree. So they had to keep adding epicycles upon epicycles. And if you're into history of science at all, that phrase, epicycles on epicycles, I guess upon or on epicycle, it's a sort of commentary on complexity of a model that you are building. And this actually happens in modern science. The greatest achievement in modern science is something called the standard model of particles. And if you talk to any particle physicist, what they will tell you is that they know for a fact that standard model is not the final correct model, even though that's our greatest achievement of the 20th century. And one of the reasons is that it has too many epicycles. The standard model has like 15 or 17 adjustable parameters. There's too many gears in the model that has to fit just right. And when we look at our attitude today is that when something gets that complicated, our intuition says, okay, that cannot be right. There has to be a better way of explaining this. And that's the sort of the same thing that was happening 500 years ago. That astronomers have been working with this theory, this framework for a long time, but they were having to add more and more complication to make it continue to work. And at some point, somebody said, all right, this isn't working. We need a new model. You need a new paradigm. And I guess there are different people who were proposing this. Actually, there was another guy earlier in the Greek era when, I forget his name. I really forget his name. But the idea that the Earth is not at the center, but the sun is at the center, it's not a new idea. It's actually a very old idea. Copernicus is only responsible for bringing it back during Renaissance, right? So he was bringing back the old classical ideas that had fallen out of favor. So this is the Copernicus's geocentric model, Copernican whatever. Wait, that's the Ptolemaic system. I want this. This is the Copernicus's not geocentric, heliocentric model. So all the writings are on the top half, so I'll show the top half. It's, I think, in Latin, but everyone has some sense of what each of those words mean. Sol, S-O-L. Like everyone here has like solar, Latin rule for sun. And here's the Mercury, Venus, Earth on the third circle. Wait, what's on the fourth circle? I have no idea. Well, here is Mars, Jupiter, Saturn. Here are the stars that's way out far away. So this is the Copernican model. And so he's the one that we usually credit with the heliocentric model of the solar system. Even though it wasn't a new idea, but he's the one who brought it back after people have forgotten about it for 1,000 years. Now let me ask you this question: was Copernicus right? As in, you take this model and you just apply it to our solar system, make some observations. And in fact, this is a hard part in astronomy. You have to sort of imagine up this model, the three-dimensional model of where the sun, Earth, and Mars are in the actual space from limited information we can get from our night sky. So it's something that actually takes a lot of math. It takes a lot of geometry to figure all this out. But imagine that you did that. You put the sun at the center, put Mercury after some observations, put it on some circle of some radius, moving at some speed. And you do that for Venus, Earth, Mars. Let's say you do all that. You make your observation for a few years. And so this is what I mean when I ask the question, is this model right? As in, you make all those observations and you would find, all the planets are where they are supposed to be. So here, let's say after having observed Mars move this way, you might predict 2 months later, Mars is going to be here. And the question of if a model is right is answering that question. If you make a prediction, will you find that prediction is confirmed by actual measurement? Anybody here know enough about the Copernican heliocentric model to answer this question? Because I sense that a lot of people want to say yes, but you suspect the answer will be no. So that's why you're not saying yes, right? Yeah, so the answer is no. Copernican model was actually wrong. In fact, here's the one biggest way you can judge if it was wrong or correct. Do you know, from your knowledge of history, if a Copernican heliocentric model was immediately accepted? No, you do know that there was a whole big debate over it, right? There were people getting burned at the stake. There were people being forced to recant Galileo. People being forced to recant whatever it is they wrote. So there was a big debate. Why do you think there was a debate?
Religion.
So there are some issues having to do with essentially politics of the time. People in power didn't want their power challenged. And in that time, that's what religion reflected, Pope and whatever. So all this actually comes with the whole, the Reformation movement, but whatever. So I want to stay outside of that. So there are people in power who had invested in geocentric model already, and they were resistant to change. But actually, when I talk about debate, so there's the debate that you hear about in the history class, and that's not wrong, but the impression sometimes you get from your history class is that was the only debate. That if the Catholic Church didn't exist, then Copernican idea would have been immediately accepted, and that's not true. There was debate within the scientific community. So among the group of astronomers, people who have no particular religious conviction whether it has to be one or the other, not everyone was convinced that this was correct. And it really comes down to measurement. So you make this prediction, right? So you observe Mars, let's say at this position at a particular time that you observe it. And you have built a model of motion of Mars, so you make a prediction. Next month, it's the same day, Mars will be here, for example. And let's say, I'm just gonna make up some positions. So let's say this purple is the prediction based on geocentric model. And let's say the Copernican heliocentric model makes a different prediction. Copernican heliocentric model makes the prediction, let me erase all these. It makes the prediction that the Mars will be here. This is the Copernican model. So I guess I should say helio. And when people measure the position of the Mars, it would, a month later, it would be somewhere like here. So as in, both models were wrong. Like we knew that geocentric model was wrong in the sense that people have been adding epicycles and trying to predict the motion of Mars. It works well, but not perfectly. There has always been this measurement error. And with the model that Copernicus proposed, it wasn't any better, at least not initially. It also had errors. Copernican heliocentric model would also predict the position slightly off, the same way the Ptolemy's model did. So that's the source of the debate among astronomers, that this heliocentric model, it wasn't any more accurate, at least not initially, than the old model that's been already around. And really, when you look at the look at the history, heliocentric model, it has I can cite one pro and one con. Like one thing that you would say in favor of the model, and one thing that you would say against the model. Any idea what the number one thing you would say against the heliocentric model? Like if somebody told you, showed you this diagram that tell you that the sun is at the center of your visible universe, and that Earth is the one, Earth moves around the sun, what would you say to that? Like what would be the number one reason you would bring up and say, I don't believe you? Yeah, it doesn't feel like we are moving, right? I mean, so for you guys, you know about Newton's first and second law. You know that Earth can be moving just at constant speed, and there, in terms of what you're feeling, there wouldn't be any difference. But you know, we're talking about people before Newton's time. They don't know about Newton's laws. But the number one big thing is that heliocentric is, it's not intuitive. It's not intuitive in the sense that Earth doesn't feel like it's moving. So it doesn't feel like Earth is moving. And there are other arguments brought up against heliocentric model. And actually, Galileo was the one that answered a lot of them. So Galileo is the one who discovered the moons of Jupiter and Saturn. I think Jupiter and Saturn, or just Jupiter? I don't know. We call them Galilean moons because Galileo is the one who used the telescope to find them. And that addressed some of the arguments against this model. Because what people were saying was, you know, you have this moon going around the Earth. So what people were saying was, as the Earth moves, doesn't it leave the moon behind? What's keeping the moon with the Earth? And when Galileo saw the moons of Jupiter and Saturn, that's when, oh, it apparently happens with the other planets too. So why couldn't it happen with the Earth? But this would be the biggest reason that someone would say this cannot be right, because it's not intuitive. It doesn't immediately agree with your gut feeling of how things work. And so let's say that's the con. The biggest thing that that you have going for the heliocentric model, and the reason a lot of the astronomers switch it to this position, even though heliocentric model was not any more accurate, was this was more elegant. It's an easier way of calculating the positions of planets. In fact, that's how Copernicus put it. I guess he was afraid of getting persecuted by the church. So he did publish it after, like posthumously after he died. And he couched his proposition very carefully, as in, he didn't say, this is actually how things are. He's saying, well, if you think of things as being like this, then it makes it easier for us to calculate the positions of planets. But that would be the biggest pro. That is, it is more elegant. Elegant or a simpler calculation. So, imagine you are an astronomer and you are looking at two models. They are both equally wrong or equally right, as in they predict the position approximately, but they don't do it precisely. And you're trying to pick between them. This is the old model that everyone has been using, but it's been very complicated. To do any calculation with this, you have to draw a lot of epicycles and do that. And I think at some point there's like 2 or 3 levels of epicycles. And you might have gotten frustrated with all that level of complexity. Then you look at this model, it looks a lot simpler. And with a simpler model, if you get about the same level of accuracy, then you might say, oh, maybe this is actually closer to the correct model than the geocentric model ever will be. Okay. So this was the scientific debate of the time. And that's how I want you to present this debate. The debate between geocentric model and heliocentric model, it's not at least it should not be debate between religion and science. I think that's historically incorrect. It's not a debate between religion and science. It's a debate between two competing scientific models. As in, geocentric model was scientific in the sense we would call it. And heliocentric model was also scientific. And one thing I want to tell you is that they're both wrong. In terms of saying the exact picture of the solar system as they are both wrong. As in, if you are a modern astronomer, You would definitely not use a geocentric model. You wouldn't call yourself an astronomer if you're doing that. And you also would not use the same assumptions that Copernicus did in building his model. So what I want to talk to you about is these two guys who, the work of the Tycho Brahe and Johannes Kepler this is where where everyone would place the beginning of modern astronomy. So the laws of Kepler that we'll talk about soon, that's the laws that we still hold them as correct today. So this is the where I would mark beginning of modern astronomy. So another way to put it is in my typical dismissive attitude, everything that these guys did, Aristotle through Galileo, they are wrong in some crucial way. It's not just the approximation, they're just wrong in some crucial assumption. So, I mean, there are things that Galileo did that, well, actually. So one thing that Galileo said, something called the principle of relativity, I guess we still hold that to be correct as long as you are careful about what you mean by relative. But so in the context of astronomy, everything up through here has some crucial assumption that's wrong. So the contribution of Tycho Brahe and Johannes Kepler, it can be divided up pretty nicely. And this is, I think Brahe actually set out to try to settle this dispute, which is actually correct. And what Brahe realized as he was trying that, he realized that the available data was actually not all that good. So, people have been observing stars for a very long time, but there's no lengthy record of observation made from a single spot, carefully kept over a long duration of time. Because, drift like this, I said a month, but that's kind of an exaggeration. The discrepancies, they start to show when you are observing these planets for years, like a decade. So what Brahe set out to do, I think from some royal grant somewhere, Brahe is the one who collected the data. He set up an observatory, and I don't think he used any telescopes. He just made the observation with his bare eyes, and he kept a very careful record for something like 10 years. So he recorded, for example, position of Mars over a long duration of time. But Brahe died before he was able to see any significant breakthrough from his data. I think from what I read about him, he did subscribe to the heliocentric model. He thought it was some version of a heliocentric model that would be correct. But he died before he saw final result that's coming from his data. And that brings us to the guy whose name we use for the laws that we are going to introduce today. Kepler is the guy who analyzed Brahe's data. And there's a very interesting story behind it. Apparently, he analyzed them in the 3 years while there was some legal dispute with the Brahe's estate after he died, whether who should get the data. And he just analyzed it while the dispute was ongoing. And he published what's called three laws of planetary motion. And that's what I want to go over. But so let me reserve some space here. But before we talk about those three laws of planetary motion, I want to spell out what kind of assumptions or laws seem to be in this model, so that it's clearer to everyone what we are correcting in the Copernican model. So Kepler came up with these three laws. Kepler's three laws of planetary motion. So before we talk about this, let's just spell out what we think the laws of Copernican planetary motion would be. So do you see any feature here that you would say this is a rule that planets must follow as they move around the sun? Tell me some rules.
Planets have a circular motion.
Planets move, okay, have a circular motion. Let's make it a little more precise. Planets, for example, Mars, moves in a circle. Specify the circle for me. Like, what are the features of circle? What do you need to define a circle?
Radius.
You need the radius, and what else?
Center.
You need the center. You need to know the position of the circle and how big it is. Where is the center of the circle? Yeah, sun at the center. So yeah, that's actually the key feature of this model. You'd say planets move in a circle with sun at the center. Good. Okay. Any other laws of Copernican model? I guess that's probably it. That's the biggest one. That's the one that's clearly visible from this diagram. Any other laws you might come up with, you kind of need more information to do that. But so that's the biggest feature that you see here. And this is the feature that I'm telling you is wrong. Planets do not move in a circle with the sun at the center. They don't. And that's the source why Copernican model always had some error. Because it started out with this assumption that was not correct. And Copernicus assumed this for the same reason that Aristotle assumed that Earth was at the center. Because Earth being at the center made intuitive sense, right? And when Copernicus began to go out of the box, start to think maybe Earth, even though it doesn't seem to be moving, maybe it's moving somehow. We are just not feeling it. He was trapped by another box. He was trapped by the box thinking that, well, what's the shape that these objects should move? He thought circle is the natural one. Some people had it like circle is perfect, so heavenly things are perfect. I don't know if he thought that, but Copernicus thought circle is the reasonable shape for this to move in. And he got somehow locked into that. And this assumption that these planets move in a circle, that's the key thing that's wrong about the Copernican model, because they do not move in a circle. So that brings us to Kepler's first law of planetary motion. So let me give you actual Kepler's laws. So Kepler's first law of planetary motion is that exactly the statement that contradicts what Copernicus was assuming, that they move in a circle. Well, from Kepler's analysis of Bride's data, what he found to be true is planets move in not a circle, but I probably should do this in a different color. Move in an ellipse. With the sun at one of the, I want to say focuses, but I'm pretty sure foci is the more common way to call it, so I'll say foci, so I want to say focuses, but foci is what most people say. Okay, who here remembers how we define an ellipse? Who here remembers how we define a circle? If you wanted to draw a perfect circle, how would you draw a circle? Like, if I go like this, it would look circle-ish, but it's not really a circle, right? Because my hand could shake, so I might have done something that makes it not exactly a circle. Like, how would I construct a circle? How would I, how do I draw in such a way that I make sure that what I'm drawing is actual circle?
We put the center and then radius and then.
Center and radius. What's special about radius?
From the center to all direction is equal.
Center, so radius is the equal distance. That is that from center to all the points, right? Is that what you're gonna say? Yeah. So, okay, I can draw this way. Let me put a dot here as the center. And I have a bunch of magnets, so I assume I can use one of, well, or all of them to put down something. Can I use this string? I guess I can. If I wanted to draw a circle, this is how I would draw it. Put a string around the pen to make sure that I'm going to be drawing out the same distance from what I'm going to call my center. And I'm going to fix this down at the center with the help of this magnet. So here's my fixed point. So I make sure it's drawn in a way that the distance from this point to all the points on my circle are the same. Like that's how a circle is defined, right? And that's how you would draw the circle. I'm kind of trying to be careful because it actually starts wrapping around and I don't want to. Something like this, right? That's how you saw circle being defined in geometry. Okay? So actually, with this definition of circle, you can actually come up with a bunch of geometric theorems about some inscribed angles and all of this sounds somewhat familiar. So this is actually the brilliant achievement of Kepler. Remember what I said about astronomy being challenging because you don't actually have a bird's eye view of solar system like this. You have to infer all of this from what you can observe from Earth. So what Kepler did is he came up with some geometric theorem that said if planets move in circle, then there's some statement he can make about motion of Mars. And I forget what the actual statement is. And when he tested the data against that statement, he found that orbit of Mars didn't satisfy that. The positions of Mars did not match with the prediction from a theorem that assumed that this circular path was the path of the planet. So what he did was he started guessing. Once he realized that this common assumption was untrue, he started sort of venturing out. Okay, if it's not a circle, what else can be? And what he settled on was, he was trying to make a circle more general. And the shape that he settled on was ellipse. Anybody here remember how to define an ellipse? I mean, you know what it looks like, right? Ellipse looks kind of like this. This is a very elongated ellipse. But how would you define it mathematically? It's not like, this is not really something you have to know for this class, but it's a useful math knowledge to have if you're going to be in. Well, okay, it's more of a math trivia, but it's still important to know the trivia. Maybe not. No one here remembers how to define an ellipse? I'll give it to you because I want to go into break. And when we come back from break, we'll do the second and the third law. So the first law so Kepler's trying to generalize. He realized that circular path is not the path. So he's trying to think, all right, what looks kind of like a circle, but it's not exactly a circle. And the shape that he guessed was ellipse. And this is why ellipse is similar to a circle. It's defined in a similar way. So to define an ellipse, you need actually 2 points. So these are what's called the foci of ellipse. An ellipse, so let me draw ellipse superposed to this. So ellipse looks like this. It has 2 points that are called focus. They are each called focus, so plural is foci. Good? Or focuses. And using these focuses, the way you define the path for the ellipse is you use the idea that was similar to a circle. You make a distance the same. But it's not because you have 2 points to measure distance to. It's not a single distance. It's more like 2 distances. So let's see. I want to have similar size. So it's more like 2 distances. So let's say so this length of the string is what we are keeping constant. So when you are drawing the path of the ellipse, this is what it would look like. You have one fixed point here, and you have another fixed point here. So the quantity that you are keeping constant would be the sum of the two distances. So let me trace out a path that's consistent with that. So let me do that in purple. So I'm going to just put this string around this. And as I try to move this purple marker, it'll get constrained by the length of the string. So, okay. Let me go back the other way. Make sure the strings don't come off. Okay, that. And for the bottom, I want to actually go down this way. Yeah. This is what an ellipse looks like. It does look a little bit different from circle, right? And you can see that it's defined in a different way than a circle. Does it look similar to a circle? Yeah. So this is why for thousands of years, people never thought to look beyond the circle. Because this is actually a fairly elliptical ellipse. As in these foci, they are pretty far apart. But even then, the resulting shape, if you didn't have another circle inside it, you might not have guessed that this is actually not a circle. So, but this key difference is the difference between the Copernican model, which at the end is not exactly correct, and the Kepler's model, which is actually exactly correct. We can derive Kepler, not we, somebody who's not even me, somebody who's good at vector calculus can derive Kepler's laws using Newton's law of motion and what we are covering today, Newton's law of universal gravitation. So before we go into break, let me just end with this. This is the difference between the Copernican model and Kepler's model. In Copernican model, you place the sun here. Sun is at the center of the circle. So this is the Copernican model, Copernicus. And the way Kepler does it, Kepler would place his sun at one of the two foci. So he would say, my sun, it's actually here. This is sun at one of the two focus. And this is the Kepler's model. Now, why one of the two? What's going on at the other focus? Nothing. It's not symmetric. It doesn't have to be symmetric. So in a planet's orbit, there's a part of the orbit that's closest to the sun. We call that perihelion. Perihelion. And in a planet's orbit, there's a portion of the orbit that's farthest from the sun. We call that, I keep misspelling this. I think it's aphelion, but I may have misspelled it again. It's called, it might be just the aphelion. This means away from the sun, this means near the sun. So, and when a planet is in the perihelion and when it's in aphelion, it actually does different things. So it's not symmetric. The sun is just at one of the two focus, why one, who knows? But there's nothing, there's actually nothing at the other focus. There's no second sun at the other focus. Yeah. So this is the model that we are going to start from and state the next to Kepler's laws of planetary motion and describe how that relates to some laws of dynamics that you already know actually. So this is Kepler's biggest discovery. Let me write down the next two of Kepler's laws, and I guess this is what I want you to think about. So, somebody tells you that this is the big discovery, and you think, all right, so I take this model, and I just have to adjust it a little bit. So this path, even though they are ellipse, you can see from here they are very close to a circle. So the adjustment I would have to make is, instead of placing the sun at the center, I'll have to just move the sun somewhere off to the side so that it's at one of the focus of these ellipses. Well, if that's what you're thinking, read these next two laws of Kepler's laws of planetary motion. The second law of planetary motion says this. I'll give you the traditional statement first, and then I will tell you a version that's a lot easier to understand. So it says line connecting Sun and a planet, that can be Earth or Mars or anything, sweeps equal area in equal time. I think this statement is a little bit difficult to figure out exactly what it means, even for those of us who have taken calculus and all that, had more math than Kepler did, in fact. So let me restate this in a slightly different way. This is how you could state it. So imagine a planet at perihelion, right? Imagine that it's moving at some speed v. Then the area, let's say over a period of 2 days or a week, this would be the area that that's swept by the line connecting from the planet to the sun. Okay? Let me actually exaggerate it a little bit. Let's say you are observing it for a month. So let's say this is the area that's swept by that line. And if you consider this planet again, when it's at the aphelion, so it's farther away from the sun. Let me get rid of the wrong Copernican sun. So it's farther away. So how do you think this angle will be different if our requirement is that it covers the equal area in equal time? Like same angle, larger angle, smaller angle. Smaller angle, right? It's like, if your pizza radius is larger, you need a smaller slice to the same amount of pizza. So that's what it says. So if the planet's moving at some velocity at the perihelion, and you look at how fast it's moving at the aphelion, and based on this picture, you would say velocity at aphelion is smaller than the velocity at the perihelion. Right? In fact, there's a even more specific relationship than that. I won't prove it, I'll just state it. So if you have some radius at perihelion, and you have some distance at aphelion, then what's said here, mathematically, it comes down to this statement, that the product of the RP and VP, product of radius at perihelion times velocity at perihelion, is equal to the radius at aphelion times velocity at aphelion. If you're trying to imagine how this might be true, this is what I would ask you to imagine. Imagine that in both cases, you are multiplying them by some duration of time delta t. Then this would cover the area, the length traveled by the planet, right? And this would cover the length traveled by the planet in same amount of time. And what it is saying is that they both have more or less the same geometrical shape. So the one measure of length times the other perpendicular measure of length, which gives you some idea of area. Imagine it's the area of a triangle as an approximation. Then this area of triangle is the same, so that makes this product same as this product. Okay? But the rule I want to boil down to is that when the planet is at its perihelion and the aphelion, we can hold on to this relationship. It's equivalent to what this statement of second law is saying, except it's a more mathematical expression that we can do something with. Okay, let me state the third of the Kepler's law of planetary motion. So the third law, it says this. So first and second law actually deals with a single planet. You could apply first law to Mars, and second law also to just Mars, right? So when you look at the orbit of Mars here, you could use the first law to say, okay, it's on an ellipse with the sun at one of the two foci. And you look at the speed of the Mars as it's going around its own orbit. You say when it's closer to the sun, it's moving faster than when it's farther away from the sun. So first and second law both deal with each of these planets individually. The third law is different in this sense. It deals with this. It compares two different planets. Specifically, it compares a planet at one orbit with another planet at a different orbit. So call this planet 1, call this planet 2. This is what the third law says. It says that the period and the radius, or the, I guess, average radius, because it's in an ellipse. So something like a radius, call it semi-major axis or whatever. So something like radius of the orbit are related. Well, how are they related? I always forget this. Let me try to get this right. So I feel like period, let me call that T, period cubed is, no, sorry, period squared is proportional to, call radius R, radius cubed. It's a very mysterious relationship. Here's one meaning I can give it to you. What would you have said if I said period is proportional to radius, or if I even said that period squared is proportional to radius squared? Like, what would you have said? Like, how would you imagine the motion of the planet so that it's consistent with these two rules? Sorry, what?
1, 2, 1.
Well, it's not exactly 1-to-1. It's two different quantities. Period is time, radius is distance. So it's not like, I don't know what 1-to-1 means. So, well, this is something that you can say. I'll just give it to you. I'm kind of running out of time. So if they were proportional like this, then what I would conclude from knowing this is that the velocity of the planets must be the same. As in, how fast Mars is moving. Look at how fast it's moving, its velocity. And look at how fast oops, that's the stars. Look at how fast the Saturn is moving. And if they have the same velocity, then this relationship between period and radius would make sense. Because you double the radius, for example, then the amount of distance you have to travel is now double. So if you're moving at the same speed, then, well, it would take you double the time. So your period would double. That's what any of these two relationships would have said. Now, that's not what Kepler's law says. What Kepler's law says is that if your radius doubles, then the right-hand side, it's octuples. It's multiplied by 8. And then you take only a square root, meaning the period actually more than doubles. So what Kepler's third law is saying, intuitive, at a conceptual level, is that if Mars is moving at some particular speed, planets that are out or in the farther orbit, they actually travel slower. So let me write it down. So this is the statement of Kepler's law, but it's a little bit hard to understand what it really means without doing a bunch of math. So what it means is that planets on larger orbit move slower. And so these are Kepler's laws. And let me ask you this question. So would you have guessed the second and third law from knowing that the orbit of the planet is actually ellipse? Like, is this something that sounds intuitively true? No, like this is like Kepler's second and third law, and probably even Kepler's first law. It's not intuitive. It's not something anybody would come up with just sitting in your own room, just thinking of how the universe should operate. And you wouldn't think, oh yeah, universe should operate in a way that the line connecting sun and a planet sweeps equal area in equal time. Like that's a crazy rule. Like you wouldn't think that should be the rule. So this is the kind of law that you can only come up with if you had the data to analyze. If you actually put in the hard work, you did the hard work hypothesizing, testing it against the data, revising your hypothesis. That's the only thing that would get you this result. And it took Kepler like 3 years to work out all of this and publish it. So I actually want to connect some of this to what you already know. So the second law, Kepler's second law, one of the benefits of doing this so late in the semester is that you have actually learned the principle of the law of nature that corresponds to Kepler's second law. So you might notice that this is the first time we're talking about this. None of the mechanics that we do actually comes from this. It's because Newton has found a more fundamental law. You already know 3 of those, Newton's laws of motion. Newton's first, second, and third law of motion. That's one of the set of fundamental laws of nature. And the second of the fundamental law of nature is the Newton's law of universal gravitation that we're going to talk about. So because we know those fundamental laws of nature, we haven't really talked about any of this because it's sort of unnecessary. But these are important, I feel, as a history lesson and what real science looks like. So yeah, I'm going to sound dismissive again. Neither of these are real science, at least they are not modern science. That's why I said modern astronomy begins here. It's because a lot of this involved a lot of philosophizing, not really testing your model against the data. And this is what real science looks like. So one of the benefits of the result like this, even though it's not the fundamental law, I can actually derive this from a fundamental law of nature. And the fundamental principle of nature is this. Where this comes from is conservation of, what do you think might be getting conserved here? Energy? Yeah, but it's going to be difficult to calculate the potential energy before I introduce Newton's law of universal gravitation. Because you have to know the form of a force. Because the distance is changing, so you have to know how your potential energy is changing. Now, does it look like your momentum is conserved? No, here it is downward velocity, downward momentum. Here it is upward velocity, upward momentum. Now, if you're looking at the momentum of the planet and the sun, they are conserved. But sun is so much heavier that it doesn't seem to be moving at all. Okay, so that leaves only one remaining quantity that can possibly be conserved. Yeah, angular momentum. So this, you can actually derive it from conservation of angular momentum. Let me multiply this equation with one quantity to help you see that. That one quantity should be, I think it should be mass of the planet. So multiply this by the mass of the planet, and that will give you the expression that you need. Let me write up the cleaned up version here. So with m multiplying to all of this, left-hand side will be radius at the perihelion times, let me group the next two quantities together, mass of the planet times the velocity at the perihelion. Well, let me finish writing it out. It looks like radius at the aphelion times mass times velocity again, mass times the velocity at the aphelion. What does this underlined quantity look like? Momentum of the planet, right? So momentum of the planet at the perihelion and momentum of the planet at the aphelion. So actually, even the magnitude of the momentum is not constant. It'll be changing. And these are what I would call, they are lever arm. As in the perpendicular distance from the center of rotation to the velocity this time. So this is a lever arm. This is another lever arm. So what does this look like? Lever arm times momentum. Well, lever arm times the force is the torque. But this is a relationship that force is to momentum the way torque is to this quantity.
Linear.
Someone other than Abdi. So how is force related to momentum? How is force related to momentum? No, not through work. Work is something to do with the energy. This is something, momentum, it's something entirely different.
Is the rate of change of momentum.
Yeah, force is rate of change of momentum. If you don't have this memorized by now, read it through the book again, because you ought to have this memorized. Force is rate of change of momentum. And torque is rate of change of what?
Linear momentum.
Not linear. Well, I don't know why you keep saying linear. So what is torque rate of change of? Angular momentum. That's the analogy. So torque is the angular version of force. So the thing that's related to torque the same way. So here the lever arm times momentum gives you, well, so lever arm times force is torque. So lever arm times momentum is angular momentum. Yeah, I keep saying to you guys, with the rotation, you really have to understand all these quantities thoroughly. If you're just trying to memorize the formulas or whatever, you're going to forget some connection. But if you understand them, this portion is relevant for your exam too. If you actually understand the quantities intuitively, then you don't have to memorize a bunch of formulas. So anyways, this quantity here is angular momentum. And the equation I've written down here, what it's saying is that, well, angular momentum is conserved. And here the angular momentum is conserved because as this planet's going around the sun, there's no external torque on the planet. Any force on the planet is pointed towards the sun. So there's no lever arm. Lever arm is 0. So that's why as the planet goes in its orbit, its angular momentum is conserved. And that's what, so that's equivalent statement to the second of law of Kepler's law. Okay. And third one, I don't think we'll have time to do this one, so I'll just leave it there. Third one, you can actually prove it. Let me give this to you as one of the homework exercises when I finally assign homework for exam 3. You can do this using standard strategy because it's a circular. So for the special case of where it's a circular motion, you can work this out for circular motion using analysis of the centripetal force. And what we are going to be talking about in the remaining 20 minutes of this class, Newton's law of universal gravitation. So this is Kepler's law. There's really one thing that's not quite satisfactory about Kepler's laws. It's not that any of it is wrong. It's not wrong. It's all correct. In fact, it's so correct. It's correct even for the things that Kepler didn't even imagine. So it's one of the things that's covered in the worksheet, I think. So this is something that shows this figure in your worksheet. Is something that shows an orbit of not a planet, but orbit of a comet. This is an orbit of a Halley's comet. How many here have heard of Halley's comet? Yeah, it's the best known comet. It's the only comet you can see without any telescope. It's associated with like end of world predictions because it comes around every 80 years or so. So every person gets to see maybe once in their life. So every time it comes around, it's never happened in my life before. So world must be ending. Anyways, so this is the path of a Halley's comet. So if you were alive in 1986. You should have seen it then. Today, 2016, it's way out here. It's way too far away, too dim for us to see. I don't think you can even see it with a telescope, even if you know where to point it at. And if you are lucky enough to be alive in 2061, you will see it again. So, I mean, if you saw it already, or you'll see it for the first time then. And this comet orbit of a comet, like a Halley's comet, actually obeys these laws of planetary motion. So it's laws of planetary and cometary motion. The comets, they move in this elongated elliptical path. And so the way all these are calculated is by applying the second law of Kepler's motion. And third one, I guess, doesn't really apply since it compares the two different things. So once again, I'm asking what's sort of deficient about Kepler's laws? And one thing that I'm telling you is not deficient in is that it's not incorrect in any way. If you're looking at the interaction between the sun and a planet or sun and a comet, this is completely correct, even more correct than Kepler imagined. But there's really, as a law of nature, there's one thing that this lacks. Really, one way where I wish this was different about this law of nature. Let me erase the board while you think about that. Like, what if there's one thing that Kepler's law doesn't quite address? What would that be? Why? Well, okay, but yeah, I can see that it doesn't. It only says that it moves in an ellipse, right? But it doesn't explain why. I don't really want to state it that way though, because a lot of the laws of nature you can always keep asking why questions, and at some point you have to say because. It's like, with the Newton's law of motion, you could say why is force equal to mass times acceleration, and I say because I don't know why. It's just the way it is. Right? So yeah. I mean, there's that, but almost any law of nature will at some point reach that point. Like I can't explain why. That's just the way things are. But so good guess. But I'm looking for something else, some other way in which Kepler's law is not quite satisfactory, but another law can be. So that's what we are replacing it with. I'm asking you to explain why. Why are we not satisfied with the Kepler's laws? Why do we have to, abandon him and go to Newton? Yeah, I have a limited amount of time, so let me just give that. So really the part that I find as a physicist unsatisfactory is actually this portion. Kepler's laws of planetary motion. Why do we need a special laws for planets? So, the sort of starting assumption in physics is that we live in a mechanical universe. And that the same law of nature governs everything. There's no law of biological motion. There's no law of organic motion versus inorganic motion. There's no law of sentient motion versus, unsentient motion. We believe the same law of nature applies to everything. Same law of nature should apply to things that are on Earth and things that are in the heaven. We believe the same law of nature that holds on Earth would hold at some galaxy far, far away, long time ago. So this is really the part that's unsatisfactory. Why special law for planets that applies only to planets and things in the heaven and not other things? So that's really what's unsatisfactory about Kepler's laws of planetary motion, that it applies only to planets. And as a physicist, what someone would want to do is there a more fundamental law that applies to everything? That we don't have to limit it to just the planet. We can apply this law to something on Earth as well. And this is the law of Newton's. So, it's right in the name. This is where Newton's law of universal gravitation comes in. So the contrast is right in the name. With the Kepler's laws, the name itself limits it only to planets. And you find that it holds for comets as well, but it's still limited. Newton's law of universal gravitation, well, it's meant to be universal. It's like you can't get broader than that. So this is the law that Newton is credited with. And I will have to tell you in the, for the sake of historical accuracy, a lot of people were thinking about this. So Newton wasn't the only one who was guessing that this might be the law that explains this. The reason Newton is important is because he was the one who could work out all the mathematics. He could work out the vector calculus stuff to figure out, starting from this proposition that I'm going to write down, that this Kepler's first law can be derived. So let me write down the Newton's law of universal gravitation. So I guess this is probably the best way to describe it. So I want to describe it with the things that's not very particular. So I think the easiest way to imagine is an artificial lab setup. So let's say you have two masses, one big mass m, small mass m. And what Newton's law says is that there's a force between this big mass m and small mass m. Force acting at some distance. They don't have to touch each other. They are at some distance away, and there's a force that attracts them to each other. And this is what Newton's law says. So there's this force of gravitation. And there are some properties about this that we can say. It's easier to say this in terms of proportionality. As in, how does force change if you change some quantity? And this force, it's proportional to how much mass there is. The mass that's producing gravity. So it's proportional to how much mass is producing gravity. And here's the second thing that's maybe not as, this is intuitive, right? If you start out with the proposition that everything in the nature sort of attracts each other, there is universal gravitation, then if there's more mass, it's probably going to attract more. Like that seems to make sense. The second thing that's maybe not as intuitive is that this force also depends on how much mass there is. So the mass that's filling the gravitational force, if there's more of this mass, there's more of the force. So this force is not only proportional to the amount of the mass that's producing gravity, it's proportional to the amount of mass that's filling the gravity. Okay? And finally, this force depends on distance. What would you guess if somebody told you there is a force of attraction between any two mass? How would you guess that this depends on distance? Like if we are farther away, would you guess that the force is greater or weaker? Yeah, weaker is a good guess. I mean, there are forces that get stronger, as in that would be something like a springs. You know, with the springs, when things get farther away, force becomes stronger. But you know, gravity doesn't feel like what spring does. So weaker would be a good guess. So once you start out with that, then you are guessing, all right, how should it depend on distance? Here's a list of choices. It could go as 1 over r. It could go as 1 over r squared. It could go as 1 over r third. It could go as 1 over r fourth. The key is you want to put the distance in the denominator. Okay? So this is where a number of people claim being the first person to come up with this guess. And you know, I'll just tell you that Newton may not have been the first one to guess it. But the common guess at the time around Newton was that it's an inverse square law, that the dependence on the distance is 1 over r squared. Okay? So this is the form of the law that Newton and several other people guessed. And Newton was the one who, based on this, was able to derive that the resulting path is indeed an ellipse. And he did a bunch of other things also. And so this, as it stands, is correct. We don't quite want to end there because all this says is proportionality. It says this force is proportional to all these quantities, but I want more. I want to be able to say, state some kind of equality. So what do I need to do so that I can replace this proportionality with an equality? Yeah, you need a constant here. Arjun, can you explain why we need a constant here? Give me one reason. Like, why couldn't I simply say gravitational force is equal to that? I don't need a constant. Like, why couldn't I do that? Why do I have to say there must be some constant here? Arjun. Okay. That's why you think we need a gravitational constant? Yeah, maybe, but not strong enough, Steven. Yeah, units. That's the biggest reason. Dimensional analysis. That's actually the power of dimensional analysis. It can tell you what piece you might be missing. So on the left-hand side, you are looking at force. That means your unit is in newtons. Or I can write this out in the basic SI units. Newton is kilogram times meter per second squared, right? Mass times acceleration. On the right-hand side, these are the units you have so far. Kilogram squared divided by meter squared. All right, that cannot be equal to this. If they don't have the same units, then they cannot be equal to each other. So you, at a minimum, you need a constant here to fix this problem. You need to be able to say, all right, whatever this is going to be a constant that has this unit. It must have a unit of Newton times meter squared per kilogram squared. That way, this will cancel out, and I'm left with a Newton. And if you want to simplify, you can put this in and cancel out some stuff, but this is the one that's easiest to memorize. Okay? So this is the unit of the gravitational constant, by the way, because that's the unit that this constant must have. And let me tell you just one more thing about the gravitational constant. It's an amazingly small number. It's so small that I don't actually have it memorized. So every time I do deal with it, I have to look it up. So gravitational constant. Yeah, so it's such a small number that Newtonian gravitational constant. All right, that seems right. Yeah, capital G, not lowercase g. There it is. 6 point. So the value of this g in this unit, the exact unit we said, is equal to 6 point, so approximately 7 times 10 to the minus 11 Newton meter squared per kilogram squared. Which means if I have a kilogram mass, and I don't have another kilogram mass. This is only 500 gram mass, but imagine it's another kilogram. So if I have these two separated by about a meter apart, then the force between them is something like 10 to the minus 10 newtons. I guess that would be 100 piconewton. Such a small amount of force that compared to almost anything, like the weight of the 1 kilogram mass alone is already 10 newtons. So compared to that, it's a very small number. So because this g is such a small number, usually the context where you would see significant gravitational force is when you have a very large number of some kind, usually a very large mass. You need an astronomically large mass for there to be significant gravitational force, which is why you feel the gravitational force due to the Earth. It's an astronomical body. And if you are on an asteroid that's big enough to have large enough mass, then you will begin to feel gravity. But on small objects like your car, 1,000 kilograms, that's not much. It produces almost negligible gravity. Yeah? So this is Newton's law of universal gravitation. I guess we don't really have time to look at the example problems that I wanted to. I think we actually have enough time for escape velocity. If I skip a step and give you the expression for gravitational potential energy. So do you guys remember how to derive potential energy? So gravity is a conservative force, right? Yes? Do you remember how to derive a potential energy from a conservative force? We did this maybe once when I derived the potential energy of a spring. So, you'll see this again in physics 4b. That's where you really need to understand this. The change in the potential energy due to a conservative force is this, minus conservative force times the displacement under the conservative force. Or you could call this the work done by conservative force. That's the change in potential energy. So with the gravitational force, you can define gravitational potential energy universally this way. You can say that if you have a mass, then very, very far away from this mass, you have zero potential energy. Not infinite, zero potential energy. And then as you fall into this mass, will your potential energy increase or decrease? If you are falling in, do you fall in the direction your potential energy increases, or do you fall in the direction your potential energy decreases? Yeah, decrease, right? So you go from infinity to some negative potential energy. Right? With that convention, this is the form of the gravitational potential energy. Gravitational potential energy, graph, is given by minus G m times big M over R. So you see some relationship to this. To actually derive it, you have to set this up, and because the force changes as a function of position, you have to set up an integral and do the integral. Look at what I did in spring force. Do something similar for gravity, and this is what you would get. Okay? So this is something that I'm ambitiously hoping I can do in 1 minute. So this is the question that I'm trying to answer. Have you heard the statement, the axiom that says, maxim, whatever, a statement that says what goes up must come down, right? I challenge that maxim and say what goes up doesn't have to come down if it goes up fast enough, right? This is more precisely, this is what I'm trying to set up. If I am on Earth, and if I have some projectile that I'm launching at some velocity, if this has enough kinetic energy, it can go out away into infinity. It doesn't ever have to come back. Okay? That speed, where it's moving so fast that it doesn't have to come back, is what's called escape velocity. And I think that's something I can calculate really quickly. So I use conservation of energy. So I'm going to say, total energy on Earth is equal to total energy very far away, right? And I'm looking for this to come to almost a stop very far away, where it has zero potential energy. So total energy very far away is zero. Yeah? Total energy on Earth is going to be this. The kinetic energy, 1/2 mv escape squared plus this gravitational potential energy. So minus g, mass of the object, times the mass of the Earth divided by r. Cancel out some things, that'll cancel out. The mass of the object cancels out, that's good. So whatever velocity that I figure out, it doesn't matter if it's a bowling ball or tennis ball. It's only the speed that matters. So let me solve for v escape here. Move this over, multiply by 2, take the square root. Then v escape is equal to square root of g big M over r. It would be the radius of the Earth. So 2 times g, mass of the Earth, divided by radius of the Earth. So if you have an object that's moving this fast, then it can actually escape the solid bounds of Earth and go out into space. Sorry, I don't remember the whole quote. Let me just plug in the numbers into Wolfram alpha and see what the number is. See if that's something that we can reasonably achieve, or if it's too large to be achievable. Yes?
Is there a square on the r?
No. So this is the formula that I'm giving you without driving. So to get this, you do the integral, and integral of 1 over r squared becomes 1 over r. But I skipped all that detailed step. But okay, so let me just plug in the. So by the way, if I made a mistake, that'll show up as I do the calculation, because the units will be wrong. So let me do this. Square root of 2 times g. Let me spell out gravitational constant, because sometimes Wolfram Alpha doesn't understand capital G. Times mass of Earth divided by radius of Earth. And let's see what we get. Make sure the mathematical understood you correctly. Earth mass times 2 g divided by radius of Earth. Yeah, nominal, equatorial, whatever. I don't really care. Approximately radius of the Earth. It says 11,180 meters per second, or about 11 kilometers per second. Does it sound like a large number? It is. Speed of sound is something like 300 meters per second. So this is, 30 times the speed of sound. Well, is this such a large number that it's unachievable? No, it's actually achievable. In fact, like space probes in space will do that. If you are moving this fast on Earth, then the friction with the air will be so much that you will heat up and burn up. So we would never launch things from atmosphere that fast. But if we launch something from outside the atmosphere, make it go this fast, then it will be moving fast enough to go far away from Earth forever. Except that there's the sun that you have to worry about. Yeah, so that's a simple calculation. That's a simple number to know. So, by the way, this is the last you will really hear of the universal law of universal gravitation. You will have some homework problems, but one thing I want to tell you is that in this class, we don't really focus a lot on this particular law, and it's because our expectation is that you will become very familiar with this inverse square law, mathematics involving this, in physics 4b, where you do static electricity, you will see this inverse square law again. So our expectation is that you will work out all the math there. So this is the one class we spend on Newton's law of universal gravitation.
So, all right, but I guess maybe I can kind of highlight this as we are doing the task that I'm actually here to do, which is to derive the expression for gravitational potential energy. So maybe let's do that. Doing that will also give you another way to be careful about how you handle directions as you're describing the law of as you're describing universal gravity. All right, maybe we should start out with description of potential energy. It's been a while, so it's good to describe the. It's good to start out with the description of potential energy, and really, it's not the potential energy itself that's defined or is useful. What is always useful instead is the change in potential energy. And the definition for change in potential energy, let's say as you go from A to B, is this. It's the amount of work done, and we want to be careful about this work done. We want this work done by a conservative force. So if an applied force is doing work, that doesn't turn into potential energy. And the work that you're doing would be as an object moves from point A to B. And finally, what's important here is that it's the minus of the work done by conservative force. You attach a conservative force doing negative work as a positive change in potential energy. Or if the work done by conservative force is positive, then that ought to be associated with a negative potential energy, because positive work done involves potential energy decreasing, so the kinetic energy can increase. So this is how we always describe potential energy. Now, there's a bit of there's a convention that I want to introduce. So this change language, change from A to B. That makes it hard to have a kind of just a simple expression for potential energy. So this is what I would love to be able to do. Love to be able to say, almost like with kinetic energy and speed. I'd love to be able to say that if I have some mass that's sitting in some, I don't know, vastness of space somewhere, I would love to be able to say that if I have some small mass and some distance, then I would like to be able to just tell you what potential energy is as a function of that distance. Just the way you can with the kinetic energy. If this object is moving at some speed, then we wouldn't hesitate for a minute to give you the kinetic energy as a function of that speed. You'll need other parameters like mass of the object and whatnot, but you can specify kinetic energy as a function of a single variable. Speed, not position. So I would love to be able to describe the function of V, a single variable. And I'd love to be able to do that with the potential energy. But as long as we are describing change in potential energy, what we have to constantly do is describe this in terms of the change in potential energy from some initial to final position. And that's very limiting, very cumbersome, very whatever. What it would be wonderful for us to be able to do is to say this change in potential energy is, say that it's potential energy at some point minus potential energy at some reference point. And come to think of it, that is what we do all the time. For example, when we are analyzing, when we are doing this kind of analysis with the potential energy being mgh, then what we always do, either implicitly or explicitly, we define where the height is measured from. So the point where h is 0, that's our reference point. Whatever the potential energy is at that point, that's our reference potential energy. We are setting this reference to be 0. And so that allows us to talk about potential energy as a function of just height, because height is measured in reference to something. And we would like to be able to do something similar here. Now, the challenge you run into is this reference going to be some context-dependent thing that unless you specify each time in a question that there's going to be ambiguity where the reference is. And in general, that's the case. That's why I led by saying it's the change in potential energy that's meaningful. Now, when you're dealing with something like a gravity, which is inverse square law, which means the gravitational force goes to 0 as your distance goes out to infinity. It turns out there's a special reference point you can use. That's a universal reference point. And that universal reference point is infinity. It's analogous to our Earth-based navigators using the stars as the reference point, because the stars are so far away. Whether you are wherever you are on the Earth, you see the same set of stars, or depending. Well, so however much your position changes around the Earth, that doesn't change your distance to the stars very much. So that's what we would like to do here in the calculation of gravitational potential energy for universal gravitation, by which I mean we are in the regime where we have to treat gravitational force as being an inverse square law. We want to treat this point A as not being some generic point A, but infinity. this is our universal reference point for gravitational potential energy. So let me do the calculation of gravitational potential energy using this as the premise. This is kind of the paradigm that I'll use to calculate the change in potential energy. Then, so then this is basically what you have. So to calculate this change in potential energy, what we have to do is we have to calculate the work done as the mass moves from infinity to a particular point, B, and work done by gravity. Once we calculate that, we can just put minus sign in front of it. That is the definition of change in potential energy. Now, from the moment you think about doing this, you should run into this conceptual problem. So we define work this way. Work done is force dot product with displacement. Now, here's the conundrum or dilemma or whatever. In this particular calculation, it looks like my displacement is infinite, coming in from infinity to some finite distance. The distance is infinite. So how is the work done not infinite? This is where you have to realize that your force is a variable. So when you are infinitely far away, your force was 0. So when you do this calculation carefully, this force dot product with the displacement won't turn out to be infinity, but instead it'll turn out to be some finite quantity. So what you have to realize here is that you can't just use this simple formula directly. Instead, you have to deal with the variable force. So what you are going to do is you are going to calculate a small infinitesimal amount of work done as the object here moves an infinitesimal distance dx. And when you make this interval dx small enough, you can say that the amount of force that's acting is it's more or less constant. Even though it's a function of r, it will be varying over a large enough interval. You say that, so imagining this this interval, taking it in from infinity, you imagine breaking this up into small enough interval that for each of these small intervals dx, you can say that that this distance r is more or less the same. So you can say that force over this interval dx is force at point r. Right? So the mathematical procedure you use to add up each one of these infinitesimal change in energy due to work done is integration. That's that's the intuition you have to develop. So here, what we are going to do is we are going to start by expressing this infinitesimal amount of work done over one of these representative intervals. And we imagine doing this for first interval, second interval, third interval, so on for really infinite number of intervals. And when you add up all that, that's going to be expressed by integral over the whole, I guess, infinite interval actually. So let's do that. Let me first write down the expression for infinitesimal amount of work done, dW. So that's going to be what will be force dot product with dx or displacement. I'm writing this symbolically up there so that I can write down the actual expressions down here carefully. So the direction of force. So So, for this method here, this is the direction of the force. So the magnitude will be simple. It'll be G times, I guess the symbols I used are small m times big M over the distance squared. That's the magnitude of force. And magnitude of dx, I guess if I'm being careful, I want to, since this r is my coordinate variable, what I want to do is I want to express this interval size in terms of this coordinate variable r. So this should be dr. That's the amount by infinitesimal amount by which r is changing. So this dx should be dr. And what I need to be careful here is this. It's the relative direction of the force and dx. So the force points inward. Good. And, oh, this is where I have to be careful. There's a joke that says a good physicist is one that makes an odd number of sign errors. No, sorry, even number of sign errors. There's a very good chance I'm going to end up making sign errors. I think what I need to do is I need to look ahead to where I'll be actually expressing this integral. So what I want to do is, so I have some sense in which how this dot product should go. This dot product here, it should give me a positive number because the force and the displacement is going in the same direction. So over this interval, gravitational force is doing positive work, which will result in negative potential energy change. So when I'm all done, when I do this integration, when I integrate this infinitesimal change over the whole interval, and that means I'm going from r equals infinity to some particular fixed point r prime, then I want this entire quantity to come out to be positive. So what I do is I make sure I choose the correct signs to be sure that's what happens. So I guess what I'm trying to get at is, so because the force is pointing towards the origin, I need to have minus sign here. That's one part. I think that much makes sense. And now for this interval portion, even though my displacement is also pointing towards the origin, I'm going to leave this dr alone. Reason being this, my interval going from infinity to r prime, that already accounts for this inward direction. And I don't want to double count for the inward direction by also putting a minus sign here. So I'm going to omit the minus sign here. And really what my check will be is that when I do this integral, I better end up with a positive number. If I don't, then I made an odd number of sign errors, and I should just fix the sign so that the final answer comes out right. This is where good intuition is useful. All right, so let me do this calculation. I talked a lot. Let me finish this math and be done with it. This is one of the I guess you still call this polynomial integral. So this is, let me pull out all the constant quantities. Constant quantities are minus g m. So what remains here inside the integral is dr over r squared, r going from infinity to r prime. This integral, hopefully everyone knows how to do it. This is a polynomial integral of this form. r to the power of minus 2 dr. So when you integrate it, you should get the antiderivative for this should be minus r to the minus 1. That should be the antiderivative. You can always double check your antiderivative by taking derivative of it. That brings down a factor of minus 1, canceling out this minus, and then the exponent changes to original minus 1, so you get minus 2. That seems right. Always double check your antiderivative when you're doing it in your head. So with that, what we get for this integral is minus g m, the antiderivative, minus r to power of minus 1, evaluated at the limit of r prime and infinity. So finish writing this out. It's minus r prime, or minus 1 over r prime, and minus minus, so plus 1 over infinity, or I mean, there's a proper way to write it. However you write it, the end result is that this term is 0. So I have this quantity here, which has 2 minus signs. So cancel out those 2 minus signs, and I end with following expression as my result of calculation: g times product of the masses divided by r prime, or the distance where you end up at. And what I've calculated is a change in it, or not change in energy, amount of work done going from infinity to that particular fixed point. And what I need to remember is that change in potential energy is minus of this. So since this is the amount of work done, what should be the gravitational potential energy, let's say at point r prime, using that universal reference point of infinity as, so where I said potential energy at r goes to infinity to 0. That's what using that universal reference point means. The potential energy at r prime is negative of that quantity. So minus g m over r prime. This is the expression for the gravitational potential energy. And this is the formula that we are using elsewhere, where we use it without derivation. Hopefully this makes intuitive sense. When you plot it, this is what it looks like. Potential energy as a function of distance r. At the very far away distance r, it's going to be 0. And as you come in closer and closer, it becomes more and more negative. So the plot of the potential energy looks like this, where it eventually approaches infinity, or rather negative infinity, as r goes to 0. R can never actually, well, it shouldn't be exactly 0 for point masses there. And I hope this makes intuitive sense. In particular, that at some finite distance r prime, that your value of the potential energy is negative. And this is how I like to make a sense of this. That imagine some mass that's sitting out at infinity. And tendency of everything is to go from high potential energy to low potential energy, if they could. So this will tend to kind of roll down the gravitational potential. And yeah, so some object that's very far away, it'll tend to move towards to an object that's gravitationally attracting it. And as it does that, its potential energy goes from 0, which is the highest amount of potential energy in this, with this particular reference. It goes down to a negative value. and it keeps going down to more and more negative value as the object goes from high potential energy to low potential energy. So yeah, this is the derivation of the potential energy formula, and there will be some context where you'll need to be able to recall this formula.